This is a short explanation for part C of the simple harmonic motion experiment. So we've got an equation here, y equals a sine omega t. We're going to try and write this out simply. So we'll start off with y. Y is our displacement. So our spring moves up and down in the y-axis. So let's draw an axis for that. We just need to understand that this equation will give us y as long as we give it the conditions. So we need to tell it the amplitude, the angular frequency, and the time t, and then we'll get a y position out, like a displacement in the y axis. Okay, so that's our y-axis drawn. So let's move on to the sine wave next. Okay, so we've got a sine function, and it depends on omega and t. Actually, let's do t. So t is our x-axis, so we're just going to draw t on there. Okay, so that's our t. That's our x-axis. So let's go with the sine wave next, and it depends on omega. So this is a sine wave, and it basically goes up to a positive maximum, then down to 0, then to a negative maximum, and then back up to 0, and continues in that fashion. It sort of draws a circle, except that it constantly moves forward. If it moved forwards from the first 0 to the second 0, and then decided to go backwards, it would actually draw a perfect circle. So that's one way to sort of think about it. Okay, so I've added a bit more to the video. This omega, to be fair, it's not the clearest omega. Okay, so that omega, for the blue line, omega is equal to 1. We've got 1 second here along their x-axis, so we know after 1 second, the wave has done 1 full cycle. So 1 full cycle in 1 second, that means we have an angular frequency, omega, which is equal to 1. This orange line, it's moving twice as quickly, so it's done 1 cycle in half the time. So we basically know by the time it got to 1 second, it would have done 2 cycles. So the angular frequency is 2 cycles per second. So when we do angular frequency, it's in like radians per second. But it's okay, you'll learn about that later. All you need to know is your omega, you find it using this equation, which you should be able to do. So just rearrange that to get your omega. And your omega is also equal to the square root of k over m. This is what relates the stiffness and the mass to this equation. So they together create omega, and then omega goes in here, and then that's what gives you this function, like the spring's motion. So yeah, hopefully this is all sort of clear. So next we're just gonna add the phase angle in, and hopefully it still makes sense afterwards. Oh, actually, before we do that, we need to add the amplitude. So we've added the amplitude on there. What the amplitude basically is the positive displacement, the maximum displacement in either direction. So positive A, let's say A is 10 centimeters. So it's going to be able to go up by 10 centimeters and down by 10 centimeters. You basically, you won't have a situation where your minimum is like of a greater magnitude than your maximum, or the other way around. So long story short, for this experiment, if you pulled it down by 3 centimeters, then your A is going to be equal to 3 centimeters. Just to recap, your omega, you calculate it using these equations, and that should be fine. Time t, you just leave it as t. Y, you just leave it as y. So we're going to get onto the phase angle now. So just before we figure out the phase angle for this experiment, I'm just going to talk you through this thing. It's called the unit circle. So if you have a circle and you say it's got 360 degrees, 360 isn't the best number to work with sometimes. So sometimes we work with radians. So if you go from 0 and go all the way around the circle, you end up at 0 again. So you can say that's 0 pi radians, or you can say it's 2 pi. So 2 pi replaces our 360 here. If you go all the way around, you could say you're at 0 degrees, or you could say you're at 360. It's more like a perspective thing. But when you're a quarter of the way, instead of 90 degrees, you would say pi over 2. And when you're at 180 degrees, you would say pi. So over here, as you can see, we've got 3 pi over 2, which is basically 3 halves. So what we're going to do now is we're going to relate this unit circle to our sine wave, and that's going to tell us our phase angle. So I'll just quickly tell you, if you see here it says y equals 0, y equals a, y equals 0, and y equals minus a. We start our cycle at y equals minus a because we pull it all the way down. So straight away we know our phase angle is going to be 3 pi over 2. But I'm just going to illustrate that for you on this graph. So if we move over here, we've got a brand new sine wave that hasn't been filled in yet. So this is with a phase angle of 0. Actually, I'm going to write these in the correct colors just so they sort of make a bit of sense. Okay, so I've just drawn some y-axes on here. So this purple one is the original axis that we used for our sine wave before. That's with a phase angle of 0. If you were to move it along like this and say, okay, start with that red line as our axis now, we'd say we have a phase angle of pi over 2. And if we start here, we've got a phase angle of pi, and over here is a phase angle of 3 pi over 2. I'll just move down a bit so you can see these clearly. But I'm going to redraw this now using the phase angle we had for this experiment, which is 3 pi over 2. Or actually, I'm just going to rub out the extra lines. But yeah, 3 pi over 2 is our phase angle because we start at the lowest point of the cycle. See here how it's at a negative maximum, the lowest point in our cycle. That's where we start. So hopefully that sort of explains everything. Okay, yeah, so you should basically end up with something like this. Just to recap, if you write this out, the only things you should actually have values for are A, omega, and the phase angle theta. So once again, A is how far you pulled down the mass. Omega, you calculate that using your experimental results. So literally just get your period and use that to calculate it. And your phase angle, I've just told you here, it's 3 pi over 2. So that's all you should need. Just mention that the time is the time and y is your vertical displacement. And that's kind of all you should need.